Hi guys. So today I'm going to show you 2.5, which is called rational functions. Okay, so you guys remember what what rational means, right? Rational is something that you can write as a fraction. Okay, so this whole section is going to be functions that are written as fractions. Okay, so the first part of this is going to be finding your horizontal asymptotes. And we've gone over this before, so this should be review. Horizontal asymptotes, there are 3 cases. Okay, so you remember the scenario where you're looking at the biggest exponent. So if you have something like x squared plus 1 over x cubed minus 2x. Okay, when the bigger exponent is on the bottom, I'm going to say bigger on bottom. What does that imply? That implies you have a horizontal asymptote at y equals 0. There'll always be one at 0 and it's bigger on the bottom. In the second case, when you have something like 3x squared plus x over 4x squared minus 2. Okay, so looking here, when they're the same, that implies you have a horizontal asymptote at y equals 3/4. Okay, so you're looking at the values that are in front of those biggest exponents. So the 3 is in front of the x squared and the 4 is in front of the x squared for the 3/4. Okay, and then your last scenario is, let's say you have x squared plus 4 over x. Okay, so this time it's bigger on top. Whoops, on top. And that implies there's no horizontal asymptote, but instead a slant asymptote. Okay, so if that is the scenario, you want to graph it to see what it looks like. Okay, to see that asymptote. Okay, so those are your horizontal asymptotes. Okay, anytime you're dealing with a rational function, you also have to be aware of vertical asymptotes. So how do you find a vertical asymptote? Okay, so hopefully you remember anything that makes the denominator 0 is going to be an issue, right? Okay, so either if you get a 0 over 0 scenario, that's going to imply that you have a hole in the graph. If you get a number over 0, that implies you have a vertical asymptote. Okay, so you'll always get a vertical asymptote at x equals whatever makes that denominator value 0. Okay, so vertical asymptotes, because it's a vertical line, you want to say where it specifically exists. Okay, so let's do an example for that. Let's say you have something that says find all horizontal and vertical asymptotes, and then graph. Of course, they're probably going to ask you to identify or state the domain. They always have to ask about the domain. Okay, so for example, let's say our function happens to be x plus 4 over x plus 3. Okay, so talking about our horizontal asymptote first. Okay, so if you're looking at our first coefficient, is it bigger on the top? Is it bigger on the bottom? Or is it the same? Okay, so this is the same. So we have a horizontal asymptote. So in our case 2, They're the coefficients that are in front of the x's, which are invisible in this case, but that's a 1 over a 1. So we have a horizontal asymptote at 1. Okay. Vertical asymptote. Do we have a vertical asymptote? Is there a value that makes that denominator 0? Okay, yes, the one value that makes the denominator 0 would be -3. And notice if I plug -3 into the top, I would not get 0. So I would get some number over 0. So that implies a vertical asymptote. So vertical asymptote at -3. Okay, so I can state my domain very quickly, just knowing that if I have a vertical asymptote at -3, it's basically all the values except for -3. So if I was going to use interval notation, I would say it exists from -infinity to -3 and not including -3, and then from -3 to infinity. Okay, so I would graph our two vertical our two asymptotes. So I have one horizontal and one vertical. Okay, so at that point, you should be able to type this into the calculator and figure out what it looks like. Okay, so I'll pull up Wabbit and type it into my y equals. Clear out my other function. I'm going to hit alpha y equals and use my fraction button to type this in so I know I'm typing this correctly. If you don't do it this way, make sure you put the top piece in parentheses and the bottom piece in parentheses, or you'll get the wrong answer. Oh, shoot. Plus 3. Okay, so once we have that in, we're just going to kind of copy that in. You can see where that graph kind of splits with those asymptotes. You can see that horizontal asymptote at 1 and the vertical asymptote at 3. So I'm just going to kind of use that as my reference to draw this. And there's my kind of hourglass function. Okay, so we're kind of basically doing that through the whole lesson. They're going to do find your asymptotes, find any holes, and your intercepts. And then ask you to graph it. And of course, state the domain. Okay. So this time, let's say my function is x cubed plus 3x squared plus 2x over x minus 4. Okay, so let's talk about our horizontal asymptotes first. The horizontal asymptote, is this bigger on the top, bigger on the bottom, or is it the same? Okay, so since it's bigger on the top, that means that we have a slant asymptote. Okay. As far as my vertical asymptote, okay, before I go ahead and decide that 4 is in fact a vertical asymptote, I want to make sure I could plug 4 in, but I'm going to take this top and I'm going to factor it so that it's going to be really easy to decide if it is a whole or vertical asymptote. Okay, so if I take the top, I can pull a greatest common factor out. I can pull an x out of each of the terms, so I get x squared plus 3x plus 2. And then I can even go further with that quantity that's in the parentheses and use the easy method. So two numbers that multiply to 2 and add to 3 would be 2 and 1. So I have x plus 2, and x plus 1. Okay, so holes are really easy to see when you factor these out. A hole would be created if you had like an x minus 4 on the top and on the bottom and they could cancel out. But since it does not cancel, that means that there is a vertical asymptote. Okay, so we have a vertical asymptote at x equals, and that would be x equals 4. Okay. It also asks us to identify holes. Are there any holes? Anything cancel out? Okay, nothing canceled, so there are no holes. Okay, intercepts. How do you find x-intercepts? Okay, to find an x-intercept, you set the y equal to 0. So if I set this y equal to 0 and solve this, the nice thing is that it's factored. The piece that's on the bottom would just get multiplied to the other side. So if I have x minus 4 times 0, that just goes away. So I ignore that piece, and this is factored, and anytime something's factored, I just set each of the quantities equal to 0, so I end up having 3 different intercepts. So I have x-intercepts at, this one gives me 0. Let's say at 0. The value that would make this one 0 is -2, and the last one would be at -1. Okay, to find a y-intercept, I just set the x is equal to 0. So if I go back to this original one, that one's going to be a little easier to just throw in an x value of 0. Quite simply have 0 plus 0 plus 0. And I'm going to say that's 0. And since it's not 0 over 0, 0 over some number, it actually turns out to be 0 over -4. The y-intercept is in fact at 0. Okay, domain, we can state that real quick. That's going to come from my vertical asymptote. Since I have a vertical asymptote at 4, x cannot equal 4. So therefore, my domain will exist from -infinity to 4, not including 4, and from 4 to infinity. Okay, so this information is all stuff that I'm going to graph before I type this into the calculator. Okay, I'm going to draw it in red. Okay, so I have a slant asymptote. I can't really draw the slant asymptote. All I know is that there's some slant going this way or potentially this way, which I'll see on the graph when I graph it in the calculator. I can plot my vertical asymptote at 4, so I can go to 4, draw that. I don't have any holes, but I have x-intercept at 0, -1, -2, and y-intercept at 0, which is the same as that. Okay, so then I'm going to just go ahead and type this again into the calculator to help me graph this. So I'm going to hit alpha y equals again since I'm dealing with a rational function. So I have x cubed plus 3x squared plus 2x all over x minus 4. Okay, so draw that and pull this over here so I can put it onto my paper. So we've got, let's see, interesting in this picture. Okay, so remember that there's supposed to be a horizontal, or excuse me, a slant asymptote. Okay, I don't really see the slant asymptote. I can see that this asymptote at 4 kind of goes down here, but there should be something on this side. The function also, if I was going to zoom in, should cross these 3 values. Okay, so it should come down, cross a -1, and then go back down after it crosses 0 and get close to that asymptote. So I can draw that side of this. But then I'm going to zoom into this kind of a weird, kind of a John Travolta-ish looking function. But there's got to be something on this right-hand side happening. So I'm just going to hit zoom out, 3, and hit enter. And man, I still don't see anything. I'm going to hit zoom out one more time just to make sure that there is something out there. Okay, so I can keep zooming out, and I think what's going to happen here, I'm going to go ahead and type in a value. This is an interesting function. And type in, I know on the other side of 4, there's got to be something. So if I hit 5, just to see where my function exists, the corresponding y value is up at 210. Okay, so if I keep zooming out, it would eventually come out to where I could actually start seeing this function. But that's an extremely steep little slant asymptote. Okay, so it should exist way up here, kind of going out. Yeah, like that. So you should be able to see that on Desmos a little bit better. Okay, so let's just do one more. Make sure that we really got this down. So we'll do the same things here. Find the asymptotes, intercepts, domain, holes if there happens to be any, and then we'll graph it. Okay, so the first thing we want to do is think about the horizontal asymptote. So in this particular scenario, everything is in factored form, and we can't tell anything from horizontal asymptotes unless it's in standard form. So if I think about if I was going to get it in standard form in FOIL, I'm just thinking about the first term. So I'd have 2x times x, which would make 2x squared for that first term. And then on the bottom, I would have an x squared plus another x, so that would be an x cubed. Okay, so is that a bigger on top, same, or bigger on bottom? Okay, so that's a bigger on bottom. So that means we will have a horizontal asymptote at y is equal to 0. Okay, for vertical, or actually let's take a look at this particular piece. Hopefully you notice that there's a x minus 5 and an x minus 5 on the top. So that is where a hole is created. So you can say there's a hole at x equals 5. The piece that's remaining is where we have a vertical asymptote. So we have a vertical asymptote. The value that would make this quantity 0 would be -4. So x equals -4. We can come up with our x-intercepts, and since this is already in factored form, I like that. I can set the top quantities, remember, because if you set the y equal to 0, the two bottom ones would be multiplied over. And since multiplying any number by 0 is still 0, I'm just looking at the top. So the top pieces set equal to 0 would be at -1/2 and +5. The y-intercept, if I plug x in, or 0 into the x's, I would have, let's see, 2x plus 1, so that would be 1. And then 0 minus 5, so that would be -5. And then on the bottom, I would have 0 minus 5 again, so -5. And 4 squared is 16. So you get 1/16. Oops, 1/16 for your y-intercept. Okay, so to state our domain, that's going to come from holes and asymptotes. Okay, so domain, we know the x's cannot be 5 or -4, so we're going to say from -infinity to -4, from -4 to 5, and then from 5 to infinity. Okay, so let's graph this one on the calculator. Hopefully this function is displayed a lot better. Okay, we have horizontal asymptotes. I'm going to draw this in red here. Horizontal at 0, which is describing the end behavior of the function. I have a vertical asymptote at -4. I have intercepts at -1/2 and 5, 1, 2, 3, 4, 5. And y-intercept at 1/16, which is pretty dang close to 0. Alright, so we're going to type this in. So alpha y equals. Okay, on the top I have 2x 2x plus 1 Dang it. And x minus 5. And on the bottom, I have x minus 5. And x plus 4 squared. Phew, finally. Alright, so I'm going to hit a zoom 6 because I was so zoomed out the last time. So let's take me into a standard 10 by 10. Alright, so there's that side. Alright, good. We can see everything pretty good on this one. So this is kind of interesting how this hugs. So you can see this side going down. So there's my vertical asymptote at -4. And then on this side, it's going to cross through at that -1/2 and come up above the y-axis. And this is really hard to see because of our pixels on the calculator. But the function just rides just above my x-axis, but it doesn't ever cross it because we don't have any more x-intercepts for it to cross through. So it's going to go, well, I guess it crosses that 5, so it goes up, it's above it, and then since it's got to cross at 5, it's going to go below it and just stay infinitely close to 0. Okay, so if you need to use a calculator like Desmos to see these functions a little bit better, feel free to do that. These are kind of wild functions. What I want you guys to do, there is more to this section, but I'm going to save it for when I get back. So we're looking at page 138. And I want you to do just 2 through 28 evens. Okay, so those problems will be due when I see you next on Wednesday, and then I'll give you the second half to this on Wednesday.